Welcome to our deep dive into one of mathematics' most mind-bending puzzles, the Banach-Tarski Paradox. Today, we're going to take you on an 8-minute journey through a world where common sense takes a holiday and math does magic. So, buckle up as we explore what a paradox is, unravel the Banach-Tarski Paradox, dive into the ideas behind its proof, and finally see how it reshapes our understanding of mathematics, all while sprinkling in a few jokes along the way. What is a paradox? Let's kick things off with a simple question. What exactly is a paradox? In everyday language, a paradox is a statement or situation that defies intuition, a kind of wait, what, moment. In mathematics, a paradox refers to a result that seems impossible or contradictory at first glance, yet remains logically sound within a rigorous framework. It's like when you find that your favorite pair of socks is both in the drawer and missing at the same time, except, in math, the socks obey strict rules. Introducing the Banach-Tarski Paradox. Now, imagine you have a solid ball, a sphere that you could, say, use as a paperweight. The Banach-Tarski Paradox tells us that you can split this ball into a finite number of pieces, and by only using rotations and translations, yes, no stretching or bending allowed, you can reassemble those pieces into two spheres, each exactly the same size as the original ball. It sounds like a magic trick straight out of a mathematician's hat, or maybe a very peculiar version of a duplicate your donut trick. Sorry, donut lovers, but in math, even a donut might pull off similar stunts. At its core, the paradox is both fascinating and baffling because it defies our everyday ideas of volume and conservation. In our regular, physical world, you'd expect that if you split something into parts and rearrange them, you'd end up with something that has the same total volume. Yet, here we are, with one ball magically becoming two full-sized copies. How did mathematicians prove it? Now, let's get into some of the nuts and bolts behind the proof. Don't worry, we'll keep it as digestible as possible, with a few jokes to ease the brain workout. 1. The role of the Axiom of Choice. The proof of the Banach-Tarski Paradox leans heavily on a powerful principle in set theory known as the Axiom of Choice. Essentially, this axiom lets us select elements from an infinite collection of sets, even if there isn't a clear rule for making those choices. Think of it as a mathematical wish that allows us to pick points in space without having to decide on a specific order. It's so magical, some mathematicians might joke that it's like having a genie for your sets, just be careful what you wish for. 2. Non-measurable sets. Using the axiom of choice, Banach and Tarski constructed sets that are non-measurable. In simpler terms, these are pieces that defy the traditional notion of volume. They don't behave like the objects we're used to. You can't assign them a conventional volume in the usual sense. Imagine trying to pour water into a glass that doesn't have a measurable capacity. Confusing, right? Yet, it's these strange sets that are the building blocks of the paradox. 3. Group theory and rotations. Another critical ingredient is the study of the sphere's symmetry. Mathematicians analyzed the rotations of a sphere and the group structure these rotations form. The idea is that by applying certain rotations, you can rearrange the pieces in such a way that they cover the sphere differently, ultimately producing two spheres out of one. It's like having a Rubik's Cube where, after a series of moves, not only do you get a solved cube, but you end up with two cubes. Okay, maybe not exactly like that, but you get the idea. 4. Piecing it together. With the tools of the axiom of choice, non-measurable sets, and group theory, the proof carefully shows that you can partition the sphere into a finite number of disjoint subsets and then, by using rigid motions, rotations and translations, reassemble these pieces into two spheres, each congruent to the original. It's a mind-boggling demonstration that challenges our very understanding of space. A few jokes to keep the math light. Now, if you're feeling a bit overwhelmed by all this abstract math, don't worry, here's a quick joke. Why did the mathematician bring a ladder to the lecture? Because he heard the topic was on a higher level. And here's another. What did the mathematician say when he finished proving the Banach-Tarski Paradox? I just split my world in two. These jokes might not win any comedy awards, but they remind us that even in the realm of high mathematics, a little humor can help keep things from feeling too abstract. Why does the Banach-Tarski Paradox matter? You might be wondering, why should we care about such a seemingly absurd result? The Banach-Tarski Paradox isn't just a quirky trick, it has deep implications for the foundations of mathematics. 1. Challenging intuition. The paradox shows us that our everyday intuition about volume and mass doesn't always hold up in the abstract world of mathematics. It forces us to reconsider what volume means when dealing with non-measurable sets. In a way, it's like finding out that your favorite recipe can be doubled without doubling the ingredients, a paradox for both chefs and mathematicians. 2. Advancements in measure theory. The result has spurred significant developments in measure theory, a branch of mathematics that deals with generalizations of notions like length, area, and volume. By showing that certain sets defy measurement, the paradox has led mathematicians to refine and sometimes redefine the tools they use to study space. 3. Philosophical and practical implications. Beyond mathematics, the Banach-Tarski paradox touches on philosophical questions about infinity and the nature of space. While these paradoxical decompositions can't be physically realized, don't try this with your soccer ball. They reveal that mathematical objects can behave in ways that are completely alien to our everyday experiences. It's a humbling reminder of the power, and sometimes the peculiarity, of abstract reasoning. 4. Inspiring further research. This paradox has inspired countless further studies and debates in fields ranging from set theory to topology. It shows that even when a result seems counterintuitive, it can open up entirely new areas of exploration. It's like discovering a secret door in a house you thought you knew inside out. Suddenly, there's an entirely new world waiting to be explored. Wrapping it all up. In summary, the Banach-Tarski paradox is a spectacular demonstration of how mathematics can defy our most basic intuitions. Starting from the concept of a paradox, a statement that contradicts common sense yet remains logically consistent, we ventured into the details of the Banach-Tarski paradox, how a sphere can be split into a finite number of pieces and reassembled into two identical spheres using only rotations and translations. We saw that the proof relies on the axiom of choice, which allows for the construction of non-measurable sets, and on group theory, which explains how rotations can rearrange the pieces in surprising ways. Despite its seemingly impossible outcome, the paradox has profound implications for measure theory, set theory, and our overall understanding of space and infinity. Before we conclude, here's one more math joke to leave you smiling. What do you call a parrot that solves paradoxes? A polymathician. Okay, maybe that one is a bit of a stretch, but we appreciate your mathematical sense of humor. Thank you for joining us on this mathematical adventure. The Banach-Tarski paradox might defy common sense, but it undeniably enriches our understanding of the abstract world. Whether you're a math enthusiast or just someone who loves a good brain teaser, remember, sometimes, even when things seem impossible, the beauty of mathematics lies in its endless ability to surprise and inspire. Until next time, keep questioning, keep exploring, and never stop marveling at the wonderful, sometimes wacky, world of math. Subscribe for more.